The NanoRig V3 is a freestanding, lightweight, autonomous rig that incorporates the main structural features of the NanoRig V2, which was designed and constructed for last year's SPET UT Drillbotics competition. In order to address challenges from the 2016 competition and adhere to the guidelines for the 2017 competition, NanoRig V3 implements a more powerful and versatile top drive motor, an advanced hierarchical control architecture with performance maps, a customized instrumented bottom hole assembly, a drill string torque sensor, and an along string sensing system. The main modifications needed to address the challenges of the rig design and performance for the 2016 competition are increasing ROP, mitigating vibrations, and improving the sensing and control system.
The structure of the NanoRig V2 proved to be a stable and reliable design, which will be used again for this year's competition. We will use water as the drilling fluid, which will be injected into the drill pipe through the swivel and collected in a mud bucket surrounding the rock sample via the pump and dump method.
In order to provide sufficient ROP and torque, we are upgrading to a 3 horsepower top drive, which is over 6 times the power of the previous top drive. The new top drive has a rated maximum speed of 1800 RPM and a maximum torque of 12 Newton meters. An accelerometer and strain gauges will be placed on the top drive to measure vibrations and whirl respectively. To address the challenge of increasing ROP and accommodate for the increased weight of the new top drive motor, we will include a new stepper motor for the drawworks with a holding torque of 2.9 Newton meters. That is 4.5 times that of the drawworks motor in the previous designs.
Now on to the drill string design and sensing. This year we will use 2 stabilizers placed 3.5 inches apart near the bit to ensure the BHA is upright at all times. An upright BHA will increase the buckling limit of the string. The stabilizers are designed to have a spiral shape which presses into the rock while drilling, emulating the effect of a screw and providing additional weight on bit.
In order to measure vibrations along the drill string, we will place 2 string gauges, one at the bottom of the drill string near the BHA, and one at the top of the drill string near the torque string. Another option we are considering is to utilize state-of-the-art fiber optics technology to measure along-string vibrations.
A downhole accelerometer, a magnetometer, and thermal sensors will be placed in the BHA to provide inclination, azimuth, and temperature downhole data for controls and analysis. In last year's competition, the main challenges for the downhole sensing suite were sensor waterproofing and reliable communication via the slip ring. We plan on using new waterproofing techniques such as conformal coating, potting, and mineral oil encapsulation. To improve the slip ring communication, we will fine-tune the communication protocol experimentally.
In order to find the optimum drilling parameter combinations, we will implement the performance map concept, which will evaluate various parameter relationships such as weight on bit versus RPM versus ROP, and weight on bit versus RPM versus vibrations. This will allow us to navigate around combinations that will create drilling dysfunctions such as whirl and stick slip. The NanoRig V3 operations will be controlled using a hierarchical control architecture. A supervisory finite state machine will guide the NanoRig V3 through the states of drilling operations such as tripping in, drilling, and tripping out. In the different states, the state machine will select set points based on the performance maps to send to the low-level controllers, which will operate the various equipment using sliding mode or feedback linearizing controls.
The real-time data will be fed into a relational database for post-operation in-depth analysis. For real-time data visualization, an integrated graphic user interface will be implemented to display drilling parameters, performance maps, and video surveillance.
In the design of any equipment in the oil and gas industry, safety is of the utmost importance. Safety features of the NanoRig V3 include graceful failure of the control system, an emergency stop button to remotely halt operations, drawworks motor brakes, outriggers for structural support, and plexiglass shields in case of debris. In conclusion, the NanoRig V3 is an improvement on a tested structural design by implementing advanced drill string sensing and design and improved control architecture which addresses challenges such as formation changes and stick and slip.